Hello everyone. Good morning, good afternoon, and good evening, depending on your location. I am Habibur Rahman, a PhD student at the University of Arizona. Our current project focuses on the utilization of in-situ resources for 3D printing in space. It's a joint project with the Department of Materials Science and Engineering and supported by the Arizona Board of Regents. Today, I am happy to inform you about our developed 3D printing technology. With this, we have been able to print several prototype parts that contain 98% of in-situ indigenous materials. This will require only 10% of the material to be carried as payload from Earth. This technology will help us to manufacture on-demand parts and components for repair and replacement. You might be wondering why this is important to us. The moon has impressed millions of people, including me. However, apart from its eternal beauty, the moon is a scientific outpost to explore the deep space into our solar system. Therefore, the NASA Artemis program is targeting the return of humans to the moon by 2024 to understand the universe and conduct more science investigations. The second phase of this program focuses on ensuring a sustainable human presence on the moon. Recently, Russia and China have announced their plans to build a lunar space station. This will need the construction of human habitats, radiation shields, and landing pads. For this, we can launch prefabricated components from Earth to be assembled on the moon. This is the usual practice for current space missions. Unfortunately, this involves major logistical challenges. Sending 1 pound of cargo to the lunar surface will cost more than $100,000. For tons of infrastructures, you can do the math. The key takeaway is that a sustainable human exploration to the moon must be supported by advanced manufacturing technologies to enable in-place construction. To address these challenges, we want to combine additive manufacturing and the utilization of native resources to manufacture parts and components on demand. I assume you are already familiar with the additive manufacturing processes. Now, let's see which lunar resources we can use. Well, the most abundant resource on the moon is the lunar regolith, which is also known as the lunar dust. It is easily accessible in multiple forms and can be collected with minimal processing steps. NASA has recently confirmed the presence of water on the sunlit surface of the moon, and water is no more limited to cold, shadowed places. We can utilize these two native resources for our manufacturing needs. To use the lunar regolith, researchers are exploring various 3D printing technologies that differ in terms of material pre- and post-processing requirements, machine setup, scalability, and autonomy of operation. For example, we can use lunar regolith with a liquid binder to form a paste that can be deposited using extrusion-based processes. Then the sintering process can remove the binder to produce dense parts. This approach is very straightforward, but also very effective in utilizing the regolith. An early attempt to construct lunar infrastructures via material extrusion was the cement contour crafting that uses the lunar cement prepared by mixing lunar regolith with a binding agent. The concept was alternative to the hydraulic concrete that we use in Earth using the water-based cement. They proposed the use of sulfur as the binder to prepare sulfur concrete. However, the low melting temperature of sulfur limits the application of lunar sulfur concrete to only the dark regions of the moon. Moreover, we have the additional prerequisite of mining sulfur in the moon, as well as potential sulfur sublimination in the vacuum environment. On the other hand, Sizarati adapted the de-shaping process to 3D print lunar regolith. They utilized two inorganic reactants, magnesium oxide powder present in the lunar regolith and a binder consisted of magnesium chloride. These two reactants undergo a chemical reaction to produce the sorrel cement. However, this process relies on the chemistry of the material. The material composition of the regolith can vary depending on the landing location of the moon. Besides, the magnesium oxide content might not be sufficient for the binding reaction. Well, earlier we saw the availability of water on the moon. So far, no one tried to utilize the water for manufacturing. We want to investigate the possibility of utilizing the water content. We are interested in a material formulation that does not rely on the chemistry of the material. For utilizing both regolith and water, we investigated the use of a hydrogel-forming polymer which is known as pluronic. The regolith can be easily and quickly mixed into the pluronic hydrogel at low temperatures. It doesn't even need any additives. The generated aqueous ink is non-toxic and it has low volatility. This ink can be used in extrusion-based processes and can be sintered to produce dense part with improved mechanical properties. This work has three major contributions. First, we developed a hydrogel-based material formulation using pluronic, water, and lunar regolith simulants that enable higher material utilization and reduces material pre-processing steps. For our developed material mix, we identified the process feasibility window in terms of printing speed and extrusion rate. And finally, we evaluated the impact of printing parameters on the print performance. Now, I am going to briefly describe the feedstock preparation and the printing setup. It's worth mentioning that because of the limited availability of lunar regolith on Earth, current research findings are based on simulants of the actual lunar regolith that are commercially available. We used the lunar highland simulant from the Exolith lab at the University of Central Florida. The as-received simulant was used with minimal pre-processing for the use in the AM process. It was added to the pluronic solution in 2 steps, with each one followed by a mixing at 600 RPM in a planetary ball mill for 2 minutes. We also carried out a final mixing to get a homogeneous mixture. We modified a commercially available ceramic 3D printer and used it for manufacturing structures and parts. We adopted this direct extrusion-based AM system for its simple design, ease of operation, and the modern requirement of operators' training and maintenance, which will come handy for potential manufacturing applications in space. Well, we have the material in hand, but to make it printable, we must ensure these 3 properties. The material needs to be extrudable and the deposition should be consistent. Second, it must retain its shape after printing. And finally, there should be interlayer bonding between the consecutive layers. To the best of our knowledge, there is no systematic research on the printability of this material. The intuition is that the material formulation has some influence on the printability because the paste rheology depends on the hydrogel to regolith ratio. Therefore, we varied the amount of regolith in the material mixture and conducted experiments for different solid contents. The literature also suggests that the printing parameters could impact the printability. Primarily, we are only considering the printing speed and extrusion rate. We conducted a preliminary investigation to identify the workable range of solid contents, that is the amount of regolith in the material mix. Then, we used an experimental design approach to find how the printing parameters and their interactions affect the printability of the material. In campaign 2, we identified the extrudability range of the material. Then, we updated those ranges to make sure that the material also has shape stability. Here is the plan for our full factorial design of experiments. We printed single layer parts for evaluating the extrudability and multi-layered parts for the buildability assessment. Across the experiments, we kept the nozzle diameter and the layer height constant. Considering the workable range identified in campaign 1, we experimented with 4 different solid contents. For each one of them, we experimented with a wide range of printing parameters. We also conducted some initial experiments by printing single tracks to narrow down the range of parameters before the second campaign. In this campaign, we printed single layers of a hollow cylinder with 15 different combinations of printing parameters. We had 2 replications to ensure that the result is consistent. Here, we qualitatively evaluated the extrudability of the material. You can see the assessment metric here. For 30 volume % solid content, you can see that we had nominal depositions for part number 14 and 15. But we had excess deposition for part number 4. Here is the color-coded summary of the assessment. Green means a nominal deposition, and red refers to either zero or excess material deposition. Yellow is the near nominal, and orange refers intermittent or high deposition. As I told you earlier, part number 14 and 15 had nominal deposition and they are green, but part number 4 had excess deposition and it's marked red. All evaluations were performed by at least 3 individuals, and we took the average of it to mitigate any potential bias in the data collection. This campaign helped us to find the extrudability window for the material. Moreover, it narrowed down the range of parameters for our next campaign. For example, we can see that extrusion multiplier 3 is producing bad parts, which will eventually show bad shape stability in multilayered parts. Similarly, 4 and 8 mm per second speeds were not giving us nominal deposition as we wanted. We will exclude this setting in the next campaign. This slide and the next one graphically show the extrudability window for different solid contents. In campaign 3, we considered 3 levels for both printing speed and extrusion rate. Speed was 12, 16, and 20 mm per second, and the extrusion multiplier was 1, 1.5, and 2. For a full factorial design with 2 replications, we printed 18 parts in total. Our goal here is to assess the shape stability of the material. Therefore, we quantitatively evaluated the deformation of the printed parts compared to our model design. Here, h and phi are the measures for deviation along the height and diameter of the multi-layered cylinders that we printed, and d is a measure for cumulative deformation. Here is a sample calculation for 30 volume % solid content. The deformation gives us a comparative assessment of the shape stability of the material for different printing parameters. The lower the deformation, the better is the shape stability of the material for a specific combination of printing parameters. In this figure, the green diamond denotes the range of parameters for which the material is both extrudable and buildable. For all the 4 solid contents, we have also identified the optimal combination of parameters within our search space. Let's recall the third requirement for printability. We wanted strong bonding among different layers. Here you can see an image of a multi-layered part after sintering. Different layers fused really well. Small pores are distributed across the whole part and not confined within the layer gaps. So we can say that our developed material is also printable because we were able to achieve good interlayer adhesion. Okay, we are claiming that we have a material and it is printable. Now you can ask me, what is the application of this printable material? To answer your question, let us recall what we will need to establish a potential lunar habitat in future. First, we need construction elements, which is the building blocks. We have successfully printed several lab-scale construction elements using the optimal process parameters that we identified from our experimental campaigns. We also went one step further and tested the compressive strength of these blocks. From our experiments, the maximum compressive strength that we received was 0.4 megapascal, which is similar to commercial ceramic foams with low density. We are still working on improving the strength of the printed parts. To wrap up this talk, we developed a hydrogel-based material formulation and identified its process feasibility window in terms of printing parameters. We also show the possibility of successfully printing several functional parts and structural elements. Remember that 90% weight of these parts will be native resources and only 10% weight need to be carried from Earth. There is still work to do. Now we are working on improving the mechanical properties of the printed parts and the scalability. Thank you so much for your kind attention. If you have any questions, please feel free to reach out to us and we will be happy to answer those.